All right, this is a group force project, Capstone project on comparing the external thermal properties between lithium ion and solid state electrolyte batteries in photovoltaic applications. My name is Seth Storino, and then our project mentor is Dr. Nicholas Rolston. Just a brief introduction. So, introduction to the project topic. So with the rise of solar, there remains an obstacle halting the energy sources of feasibility and endurance, batteries. Batteries conserve the power provided by solar panels during pre-peak hours of sunlight. So during peak time, the batteries they don't supply the power, but the solar panels do. And then disperses the power when the solar panels are not at optimal efficiency, which is during the night or during the evening. So lithium ion batteries are the current status quo of what the industry uses for battery source. And the cons to lithium ion batteries are their flammability, unstableness, and subpar levels of efficiency. Solid-state electrolyte batteries, on the other hand, they're a potential substitute for liquid electrolyte batteries, such as lithium-ion batteries, because they have a solid ionic conductor, which makes it more safe for usage and more energy efficient, and they typically have a higher ionic conductivity, as we will see. The project objective and scope is that the Rolston Battery Lab group, which is us, intends on showcasing the advantages of solid-state electrolyte batteries over liquid-state electrolyte batteries like lithium-ion batteries through high and low ambient temperature testing. We will also show a prototype at the very end of this demonstration. And yep, the team will communicate its experimental and simulation results through the physical proof of concept as well as modeling simulation. Lab research. So for the research portion, we used an EIS, electrochemical impedance spectroscopy for the solid state electrolyte sample, the LLZO sample, as you can see on the left-hand side. And we did heating through room temperature to all the way to 100 degrees Celsius. At the very top over here, you can see the diagram. The diagram shows what the EIS looks like. And then for the biologic, we use that for discharge and charging the temperature, or sorry, charge and discharge testing. And we use the MOLY-cell battery for that as well. So for the EIS test, this is the 25 to 100 degrees Celsius. And you can see here for the semicircle that this is what shows the ionic conductivity. So the semicircle shows ionic conductivity. So as the temperature increases, so does ionic conductivity, which is what we expected for the LLZO sample, which is a solid-state electrolyte battery sample. For the modeling portion, this is the equivalent circuit that we're using. So we have the RO, which is the internal resistance, and the R1, R2, C1, C2, that's the two-time constant. And then for the test we ran for the modeling simulation is a standard capacity charge and discharge, which is what we use for the biologic battery chamber, and then pulse tests such as the hybrid pulse characterization tests, which is what we used for the MATLAB Simulink model. So this is the model that we derived for the lithium ion battery. This is a liquid state electrolyte once again. And this is the model that we derived. And then this is for the biologic charge and discharging test data at -10 degrees Celsius. This is using the MOLY-cell battery, which is a liquid state electrolyte battery, also a lithium ion battery. And you can see in the table the charge and discharge test rate. For the prototype, we have a prototype diagram. This is a solar panel. We're using 3 in series connecting to a solar charge controller with a battery. This is going to moderate between the peak and non-peak hours so that during peak hours, the solar panel is running, but non-peak hours, the battery is running. And then the buck converter, this is stepping down from 24 volts, since that's what the battery is, all the way down to 12 volts. And then the inverter is converting from DC to AC. Input is 12 volts. That's what the buck converter is for. And then the load will be an AC load, such as a lamp, which we'll see in the next slide. So this is our lamp. This is our prototype, I should say, from what you see in the diagram from the previous slide. So you can see the three solar panels in series with the solar charge controller in the middle, and then the lamp is the thing that's turned on right now, and that is our load. And then our battery, like I said, is 24 volt, roughly, and then the buck converter, and then connecting to the inverter to the load. And also we measured the solar panel to see what capacity they run. So on the left-hand side, three solar panels in series run about 41 volts. And the current on the right-hand side is 234 milliamps for the total three, which makes sense because in series, solar panels increase in voltage, but the value stays for current. Thank you and have a nice day.